The sample on your screen shows a common combination of structures where we have a planar surface, a fault surface, a slicken side if you like, which has on it a linear feature here, these slicken lines, and those show the direction of movement on the fault surface. So we could measure the orientation of these slicken lines by plunge and trend, but because they lie in a planar surface, it's often convenient to measure them by what we call the rake, sometimes also known as the pitch. So the rake is the angle measured in the surface from a horizontal line. That horizontal line would be the strike. So I'm going to put a compass on the surface here, and I'm going to make sure that that pendulum is hanging directly downwards, and I'm going to draw a strike line on the surface. I need to make sure my compass is touching the rock, and I have a piece of chalk here, so I've drawn a strike line on the surface. Now the rake is most easily measured with a protractor, although you can measure it with a compass as well. And you'll see here, if I put my piece of chalk parallel to the lineation, that the rake of those linear features on the surface is about maybe 140 degrees or thereabouts. So we have a rake of 140 degrees, and the question is, can we convert that into a plunge and trend? So we're going to go over to the wolf net and bring it to the front. And let's say the strike and dip of that plane was strike of, let's say, 117, and it's quite steeply dipping, so we'll say that the dip is 68 degrees. And then the rake of our line was 140 degrees. So we'll do what we've done before and rotate the net into a position where we can measure 117 degrees for the strike. Here we go. There we are, and we'll draw a great circle using this curve tool here. We're going to start at the edge of the net. I think I'm going to zoom in a little bit for a little bit extra accuracy, and we want to make sure the dip is 68 degrees that we're representing, so just before that 70 line, click, 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 click. And double click at the end. There's a great circle representing the plane 117, 68. And now we need to position our x representing the lineation correctly on that plane. So if the lineation was exactly parallel to the strike, it would plot here, or alternatively over here. But because it's raking, we have to count the number of degrees of rake along the great circle. So that's 20, 30, 40, 50, 60, 70, 80, 90 is straight down the dip, 100, 110, 120, 130, 140. So our point representing the orientation of that lineation has to go just there. So we've plotted the orientation of a line by rake. Now we can return the net to its starting position, and there you can see both the plane and the line. We could see about converting that rake to a plunge and trend measurement. So in order to do that, I need to put the straight radius that goes through the arrow through that point on the net, and it looks as if I have to rotate the net to 279.4 or thereabouts, so we'll say 279 to the nearest degree. So the trend is going to be 279, and then the plunge of that line is found by counting in from the primitive 10, 20, 30, 7 degrees. So we've converted the rake of 140 degrees in that plane to a to get my text box here. Try that again. 279 degrees of trend and 37 degrees of plunge. So remember, it only makes sense to measure a rake when a line lies in a plane. But if you do have a line that does lie in a plane, then you can get away with making one less measurement to constrain its position. You just have to make one more measurement, the rake, and you have fixed its position in 3D space. And if you need to convert it to a plunge and trend, you can do so with the stereographic projection.